Another technique is called momentum. So momentum, it takes some inspiration from physics. So the idea is that if I'm going down a slope and all the gradients are pointing in the same direction, then my speed will increase because of the acceleration. And when I arrive at the bottom, my speed will decrease because now the gradient is not pointing down anymore. So we must interpret it as potential energy. So the potential energy is mass times the gravitational force from the elevation at one position in my parameter space. H, the elevation, will be the value of the loss. And the force will be equal to mass times acceleration, and which is equal to minus the derivative of the potential energy at this location. And if I take the derivative of this function at point 8, these two are just constant values. I take the derivative of h with respect to h, so I obtain this. And now we will try to simulate this physical system. So I will discretize time, and I will compute one term associated to acceleration, one term for the speed, and one term for the position. And so I will compute at time my value at time at by using this formula, ma equal m this. So I just divide by m, and I just have minus g derivative of h at point ht. With the acceleration, I can multiply it by the discretization of my time, delta t. I add it to my previous value of my speed, and here I can have a coefficient mu to represent the friction. In delta t, I lose some of the speed due to some friction, and I'm adding the two. And now I'm updating the position with the position plus the speed times the time discretization. In optimization, we will remove the delta t. They will be equal to 1, and I obtain these three equations, and I will combine this and this one. And now I have my gradient descent with momentum algorithm. So I will simulate with this equation of physics the fact that I'm accelerating if my gradients are pointing in the same direction at each iteration. So I start here. You can see that I have some momentum that I will overshoot. I will go up. Then I slowing down, a little bit of overshooting here. And so this algorithm is not very good on this function to find the minimum, because I don't have enough friction term because of this overshooting. I'm taking too much speed at the beginning, and I will miss the minimum. And this algorithm is not a descent algorithm. Because of the speed that I'm taking in previous iteration, the new direction that I will obtain, maybe it's not a direction that will decrease my loss. Maybe it will increase it. So we can see here that the loss will increase because I have too momentum, but then it decreases, too much momentum, and I have this oscillation. So it doesn't seem to be a promising algorithm, but we will see for other landscape. So this one is, I just found the best values to optimize this one. So it's super fast with momentum. And we cannot see really the beautiful dynamic of rolling down the surface because my learning rate is too high, so I'm bouncing in the parameter space. And here what is happening is that at the beginning I have a strong gradient in this direction, here. Then I arrive on this side, and the gradient is in the opposite direction. But because of the momentum, now I have two contradictory gradients. In first iteration, it was on this direction, second in this direction. So I land in the middle here. And here, the gradient will be small for this direction, and I will have a little bit of gradient in this direction. But still, I still have my momentum coming from the previous step, so I overshoot a little bit. But then I will converge more quickly to the optimum than the pure gradient descent. And we can see the difference here, because the gradients are contradictory. They will cancel out. It will reduce the speed. And instead of just bouncing from one side to the other, because they cancel out, I can stabilize a little bit the dynamic on this loss function. And so with these two concepts, you can interpret many algorithms in deep learning that have been proposed for deep learning. And now the most famous one that everyone uses by default is Adam. And Adam combines the two ideas, the idea of preconditioning and the idea of momentum. So here we have the same equation as before, the preconditioning term. And here we have the equation of the momentum. So they are just two moving average over time for these two quantities. And instead of using the gradient here, I'm using the momentum term. And also I will precondition. So these two equations together with this optimizer, you can already optimize well in deep learning. I recommend always to use Adam at the beginning to be sure that you can optimize the function, be able to learn on your data, to minimize the loss function on the training set. And yeah, it's a good optimizer. Do not implement these three equations directly. There are two other equations that I did not cover. It's only because there's a problem with initialization of M and V, and we must correct this problem. It will induce a bias in this quantity, and we must correct this bias with two other equations. But it's not really important, it's a detail. Here.